So in today's lesson 7.4, Foundations of Math 30, we're going to talk about characteristics of log functions, logarithmic functions, I'll abbreviate that to log functions, with base 10, and log functions with base e, and they have a special name which I'll talk to you about a little bit later. So I don't know how many of you have been through chemistry. In the textbook here, it talks about a story where this guy, Randy, came across a new type of function. And here's the function over here. It would look something like this down here. I don't know if you can see that or not. But it's got this funny log, okay? This is not a tree log. This is short for logarithmic. And it's a certain type of function. So if we go back here, what did Randy notice? He learned that in chemistry that the pH of a solution is determined by a logarithmic function. Okay? So that's maybe something, if you've been through, how many of you have been through chemistry here? Put up your hand. Okay? Been through chemistry. Okay? Accompanied by faces like this. Sorry. Okay? But if you've been through chemistry, you would know that pH, right, which is the measure of acidity, or really the pH stands for the negative log, or the logarithm, of the concentration of hydronium ions, or H plus ions. So this is how you calculate pH, the measure of acidity. And it's usually from 0 to 14. This is very acidic down here, and this is very basic. So there's a lot of ions if the pH is low, a lot of hydrogen ions if the pH is low. And we'll find out why that is, okay? We'll come back to this maybe a little bit, but that's how you find pH. So there's a connection to chemistry there, and we're going to study these log functions here, okay? Logarithmic. Now, before we get too far into it, I think that it's easy to explain log functions when we talk about our exponential functions, okay, that we've already talked about. So everybody look at your calculator. Now, you can have your scientific calculator out, or you can have, this graphing calculator that you'll have right now. But I want you to notice something, that there is a function, there's a 10 to the power of x function on your calculator. See that? It's a second function here, right here, 10 to the power of x. Notice what the function that it is related to. Log, L-O-G, okay? Down here, look at, we have e to the power of x. So that's an exponential. And down here, the function that's related to that is ln. Okay, so these are both log buttons, okay, logarithms. The e to the power of x, the one that's associated with that, the natural logarithm. It's called the natural logarithm. Again, I mentioned the other day, I think I mentioned to you guys the other day that e, a base e for an exponential function, is very, very convenient to use for exponential growth in calculus. And so that's why e is on all your calculators, because it's a very special function for calculus. Now, with every exponential function, the inverse function is a logarithm function. So if you guys notice, look at square root here. I know it might be, it's a little small to see from the back row there, but look at squared and square root. Do you see how those are inverse functions? Those are opposite functions. Squaring something is the opposite of taking the square root. Does that make sense? What else is on our calculator? Okay, sine. If you have sine of an angle, to get rid of the sine or to undo the sine function, the sine part, you take the inverse, sine to the negative 1. What else is really good here? Okay, well, I don't notice too much else here, I guess. X to the negative 1. Okay, so if you have x, the inverse is x to the negative 1, but it doesn't show an inverse on the same button. So, anyways, what I'm getting at is that the logarithm, okay, the logarithm function, is the inverse of an exponential function with base 10. Okay, and we're going to show that by actually graphing this now. Okay, so get to your y equals screen. Make sure the plots are off. So if they're highlighted like this, that's no good. So go up there and just deselect them. And I'm going to get you to type in here, let's see, 10 to the power of x. Okay, so that's a exponential function to the power of x. So let's go zoom 6. just to get to a standard window and see what that looks like. Okay. All right. So we're going to zoom in a little bit here. So let's change our window here. Maybe move your window to something like this if you want, and we'll all be on the kind of the same screen here. So -4, +4, -4, and 10. We may adjust this a little bit later, but if we're graphing this exponential function, it looks like this, and that should make sense to you because we've studied exponential functions close to 0 here, right? And then y equals 1, it goes through, and then it rises fairly sharply because 10 is a larger base than 2. So what I mentioned was that the logarithm is the inverse of an exponential function. So if you're taking a base like 10 and you're raising that base to a power of something else, something unknown, something x, then the opposite of that, to invert that, would be to take the logarithm. Okay, so let's just go to the next one, the next y equals, and let's put log of x in there. Okay, and these are related by an inverse relationship. So let's just see what that looks like. Okay, so you see it comes down here like this, and it stretches up here. Okay. Now, I am going to adjust this window a little bit here now, because this doesn't look exactly like I want, because this is 10, I think, and this is only 4. So let's bring this one down, the y max, let's bring that down to 4, so we can see both of them sort of similarly. And let's see what happens there. So there's our 10 to the power of x, and here is our log to the power of x. Okay, so what we see here is a couple things. I want you to see a couple things. The y-intercept here is 1 for our exponential function. The x-intercept here is 1 for this function. So if we just tested that, second function, calculate, enter, let's do x equals 1. And we get 10 for this function, and if I use my cursor to go down to this function, I get 1, 0. See that? So that's our x-intercept. Okay. So what about if I did x equals 2? X equals 2, for 10 to the power of 2, that would be 100. Okay, and what about for the other one? 0.30103. So I guess what we want to talk about is, how is this number related to the other number? And I don't know if you'd notice, or how many of you have ever heard of graphing inverses, how we do that. I think we did that in pre-calculus. I don't know if anyone was in pre-calculus. Have you ever heard me say, well, I guess in chapter 5? Inverse and reverse. Have you ever heard me pair those together? Inverse means reverse. You ever heard that? We talk about that? Inverse, reverse? Okay. So that's what we're looking at here for inverse functions. So let's just copy down some notes here. Let's write down some notes. Okay. Y equals log of x, and this is going to be logarithm with a base 10. You don't see the 10 there written because this is called the common logarithm. Okay, so this is the common logarithm because it's base 10. And y equals 10 to the power of x is our exponential function. And these two are inverses of each other. Okay? Okay, so they're inverse. Now, when we're graphing inverses, we think this little phrase. Inverse means reverse. Okay? Inverse means reverse. And what are we reversing? We're reversing the x and y. So that it kind of looks like this. When you have an inverse function and you're talking about how to graph it, you simply switch or reverse the xy. So let's just kind of flesh this out a little bit. If we go back to our calculator, okay, 0, 1 for this one right here becomes 1, 0 for the log. Does that make sense? 1 becomes, let's see, 1. So 1 is 10, right? 10 to the power of 1. What about for the other one? Sorry, 1 and 10. So let's check 10 with the other one and see if it's 1. So we'll go to enter here, and let's check 10. Oops. Oh, I guess 10 is not on my screen. Maybe I can't do that. Okay. Going to fix that x max so that 10 is on the screen, okay? And again, you can just watch. You don't have to do this. I'm going kind of quick here. But we already said that 1 should be 10. So what about 10? We were thinking if this is really an inverse, 10 should be 1. So let's just check that. Okay? So here you go. On the other graph, it is. They're reversed. Okay? So you'll find that every point is reversed on an inverse graph. So if we're to sketch this, so y equals 10 to the power of x, kind of looks like this, right? We're going through 1, and it rises fairly sharply. The log, then, is everything is reversed. And how we can think about that is that this graph is reflected about this line, y equals x. So whatever point you find, if you reflect it about this line right here, or around this line right here, that's where your other point is. So 0, 1 becomes 1, 0. This point here, okay, you think about a reflection, like a mirror, it's down here. This point over here, reflected through the mirror, is over here. This point that's really close to 0, reflected over here, really close to this one. So if you connect those points, you get something that looks like this, ish, and that's your inverse. Okay, so graphs of inverses are related by reversing the y and x, and it looks like it's a reflection about this line that's y equals x. That's made up of 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. Okay, so the graphs of inverses are reflected around this line, and if you're looking at tables of values, you simply switch x and y. And we can see that. Let's go back to our, let's go to our text here. Okay, so what page am I looking at? I'm looking at this page right here. Okay, so look at this. This is sort of what we just drew right here. And this is in the summary, but this is sort of where we're at. Okay, here's the y equals x line. Here's y equals 10 to the power of x. Here's y equals log of x. All right, so they're a reflection. If you look over here, if we talk about E, then really E is a very similar shape to 10 to the power of x, but it's just a different base. And remember, it's somewhere between 2 and 3, right? And so this one is called the natural logarithm because E is a special number. So if we go back to our notes here, y equals e to the power of x, and y equals the natural logarithm of x. These are inverses as well. Okay? These are inverses of each other. And the natural logarithm of x, we usually just do ln, which is sort of the abbreviation for the Latin Logarithmus naturalis sort of thing, so that they have the L first. Natural logarithm, logarithm, natural. And this is what it means. It's a logarithm base e. Okay? That's another way to write that. So it's still a logarithm function, but it's base e. Okay. Okay, we're going to take a look. We're going to take a look here now, a little closer at e to the x and ln of x. So here we go. We could also actually put in here y equals x line. We could put that line in there. That's right there. So you see how this is everything is a reflection. It's exactly the same distance at a 90-degree angle to this reflection line. So you go straight to the line. You go the same distance the other side. Okay, every point straight to the line. Keep going. It's exact reflection. But what I wanted to show you here is what happens to a logarithm function if we have something other than 1 for an a value, because that's on example 3 we talked about what happens there. And if you think about it, you're taking every y value, like every value that's on this blue line, and you're multiplying it by whatever number is in front. So here it's just multiplied by 1. So let me just quickly get another y equals ln of x here as reference. Okay, so that's going to be the same line. Now what happens if I move this a value, make it bigger? So watch what's happening. Every y value is being multiplied by the factor that's in front. So in this case, right now I've got, let's say a equals 3. Okay, so this y value was 0, right? Y equals 0. So 0 times 3 is still 0. Okay. What about here? Okay, so I've got about, let's go to, where's 1? Okay, so 1 is going to be right about there. Okay, and if I multiply that by 3, if I go straight up, I should be right around 3. See that? Okay. Now I don't think we'll be looking at a values that are negative, but let's just see what happens. Okay, between 0 and 1, see, this is what happens. It's really everything we studied about the exponential functions, except now it's sideways, right? If you tilt your head sideways, it's the exact same that we studied with the exponential function. So you get closer to 0, it kind of goes like that. And then, of course, negative would be a flip like that. Okay? Everyone see that? So the a value affects the graph by it multiplies all the y values by that same factor. So let's just jot down that for a summary. Y equals a times e to the x. The graph of y equals e to the x is stretched by a factor of a. In other words, i.e., that's an abbreviation for in other words. In other words, all y values of y equals e to the x are multiplied by a. So you have your original graph, and then it's right at the very end, once it's all evaluated, you multiply it by a, and that's your new one. Okay, so largely, I just want to explain to you sort of what ln means. I want to explain to you that log and an exponential function with the same base are inverses of each other. So this log, the common logarithm, is understood to be base 10. So those are perfect inverses of each other. If you had y equals 7 to the power of x, then log base 7 of x would be its inverse. Okay? So we're going to be matching graphs and stuff like that. Let's just take another quick look here at the in summary page, all right? So let's just go over this real quick. A log function has the form of f of x equals a times log of b, where b is the base, x. Okay, and we're going to study functions where b is a positive, it's not equal to 1, a is not equal to 0, and so on. And a and b are real numbers. So we're looking at positive numbers for these. All log functions of this form and of this form have these characteristics. So as we mentioned, according to our graph, and let me just see if I can do this. Let's get them both on the same page here. So these log functions here, I'm going to have to decrease this, I think. Just a little bit more. All right, so sorry if that's super small. Sorry, I'll read it out for you. But the x-intercept for log functions are always 1, okay, when they follow these cases here. They're not shifted, they're not moved up or down or left or right, okay? They have an intercept of 1. The number of y-intercepts, so notice over here that this kind of comes close to the y-axis but never ever touches it or crosses it, okay? The end behavior, the curve extends from quadrant 4 up to quadrant 1. Always. They all have the same characteristics. The domain is not all real numbers, but it's everything greater than 0. So again, sort of the flip of the domain and range for the exponential. And the range now is all real numbers. Y equals all real numbers. It can be anything from negative infinity down here to way up there to all the way up to as high as you can go. Okay? So and then these graphs here, okay? So in increasing logarithmic function, that's increasing. This is decreasing. And there again are your pictures of the reflection points. Okay, do you have any questions? Any questions for me right now? Any questions? Yes, no? Okay. I'll just give you your assignment in a second then and let you get going on that. Okay, so just a note too, in number 4 here, they are going to get you to explore a negative log of x. So they will be talking about what happens with a negative, and I can just show you that here real quick on Desmos. So if a here goes into the negative, okay, what happens then is it flips about the x-axis. So there's -1. There's an exact flip right around this x-axis here. It's like the x-axis is the mirror. Okay? So you can think about that when you do number 4 as well.